Good afternoon. My name is Rick Smith, and I'm the group leader here at the Naval Surface Warfare Center in Panama City, Florida, the group leader for computational mechanics. Today I'll be spending a few moments going through parts of this presentation that are not in the accompanying paper, try and make it a complement to the document. And I'd also like to recognize my co-author, Jeff Wright, who contributed to this work as well. The outline that we'll be using for this talk is the following. First of all, I'd like to, again, as something that won't be found in the paper, talk a little bit about our motivation for doing the work. Spend a moment talking about some high-performance yacht sailing classes that are currently being used. Talk about our algorithm a little bit, fluid, structural, and how we tie the two together. And give some results for the AC75, which is the current America's Cup yacht class, where under some nominal conditions that we sort of thought were reasonable, and compare some of the integrated aeroelastic properties of that simulation and that analysis. And some final thoughts at the very end, and a few brief words on future work. As far as motivation goes, I think it's honest and fair to say it's mostly curiosity. As a person who's worked as a naval architect his entire career and has been a sailor for as long, I just have some curiosity about what does the workflow look like within an America's Cup design setting. In particular, what does their sail design workflow look like? Are they doing any aeroelastic analysis of their sails? Or are they doing mostly sort of production CFD, FEM style work in their design cycle process? So that's the curious part. And our contribution would be applying our aeroelastic algorithm to that problem. There's a fluid method, which it's geometrically conservative finite volume method is what we'll be using and have used for a while. The structural method is a geometrically nonlinear plane stress element. The mesh update method is a hybrid scheme where we use both algebraic and elasticity-based procedures to couple through mesh movement the fluid and the structure together. And finally, under motivation, I'd just like to say this type of work and this type of public appearance can provide provide an entry point for the next generation of people coming after my generation, in particular for students and sailors as a way into the engineering and naval architecture associated with sailing. So with that, just one slide to describe some of the current high-performance sailing yacht classes that are in the world today. The one we'll be talking about today is the AC75 class, which is making its debut at the very end of December 2020. So it's essentially a few weeks from making this video. That class is shown in the far right image of the frame. Other classes which are currently still in service and being raced. The Formula 50 or the F50 class, that's a new one that was introduced about 2 years ago. The AC50 class, which was, I believe that was in Bermuda, and the AC72, which was in San Francisco. And a little history there in the lower right corner, that's the C class where most of this stuff derives from, and that's a picture taken about 40 years ago, around 1980. Okay, here we go. Okay, regarding the fluid method that we use, this is sort of our, I guess you could say it, our advertising image of the types of work that we do here in Panama City. The work is, this work shown here is done using our current incompressible flow solver, which is a face edge-based finite volume scheme. It's geometrically conservative, so we can use it on a lot of moving boundary deforming grid problems. And there are just a few recent examples of the things that we've done. A lot of free surface work, a lot of rigid body dynamics work, and some fluid structure interaction, which we'll be talking about here today. So that was the fluid method. The structural method that we bring to bear here is a geometrically nonlinear structural solver, and that solver uses, for this application, a 4-noded plane stress element. Again, it's a small strain, large deformation implementation. It uses the total Lagrangian formulation. We also implement a modified material model so that we always have a tension field within the fabric of the sail, in this case, at all times. And again, just a few things here, some test cases and recent application. This is essentially an airbag in a fluid on the case that's shown. To tie all this stuff together, we use a mesh update method, which, as I mentioned earlier, is a hybrid scheme that is a combination of a local interpolation near the wall, and that's algebraic, and that's tied to a partial differential equation based scheme for tying it all together in the bulk. And so this is the so-called plate in the box problem. It's a lot of deformation in the grid, a lot of movement at the boundary, and it's very constrained, but the scheme works fairly well to hold together here. Okay, now moving on to the presentation of our AC75 aeroelastic simulations using the Euler equations for this talk, not the Rand's equations. First of all, before we show any results, I just want to make sure everyone had a clear understanding of what we characterize as nominal conditions in the paper. There are nominal geometric parameters, that is the shape of the sail. Some of that's controlled by the class rule. Some of it is controlled by some guesswork on the part of myself and my colleague on what the sails actually look like. And so when we say nominal geometric parameters, for example, we're just talking about some assumptions we made regarding the mast mainsail system for the AC75 and how it's used in practice. There are also some nominal elastic parameters that we use as well, and that those are associated with the elastic modulus of the material and a few other things, pre-strain, et cetera, that we throw into the simulation that we think mimic what actually happens on the water. So we have here some results from our aeroelastic simulation for the AC75 mast mainsail work. And what we see here is essentially the iteration procedure being shown essentially as a time-like parameter, starting from an initial guessed or estimated solution for the nominal sail shape under nominal parameters. And I'll draw your attention to the upper left image, which is a cross-section at the mid-span. That's what the sail cross-section looks like. For those that are familiar with sailboats or sailing, you'll recognize that as not being at all conventional. It's got two surfaces. It has a leading edge, rigid leading edge mast, D-section, which is followed by two sail fabric membranes that share a trailing edge. And so we just show this here as the convergence. We just show this as the convergence from the initial case to the final case. Close up very briefly of the trailing edge. And there's an instability in the solution that manifests itself as a collapse of the trailing edge, and we'll show that, and then we'll move on. You can see the last panel of the sail is collapsing, and that causes a fair amount of difficulty that we would like to address in the future. Just some comparisons that are in the paper. I don't have time to go into those now. Finally, a coda or the ending thoughts. There is a trailing edge instability in our work. We're going to be implementing a contact method to manage that instability in the future, and it'll give us an access to a wider range of aeroelastic parameters. Future work will include Rand's equations and more realistic elastic boundary conditions for the sail. Thank you for your time and attention, and happy holidays.